So we need to worry about event ordering or serialization. So let's review that just a little bit with this example over here. Again, assuming all variables starts with 0, x and y. In this case, let's assume it's sequential consistency. And in P1, we have a write, x equal to 1, and a read, loading y into R1. And let's say we observe the value of 0. On the P2 side, we have update to y and read from x. Now, because this is sequential consistency, the fact that reading y equals 0 is not 1, that means it happens before the write, this operation on the P2 side. So it's ordered in that way. And because it's all globally ordered, so x1 has to happen, the write over here has to happen before the read over here. So x cannot be 0, it has to be 1. So let's imagine what happens if I have my simple write-back cache processor. These two processors are on the bus. Y equal to 1. That's a write request. It can be, quote, finished in P2. Okay. Well, I don't have the background. I don't have the bus. I'm requesting it in the background. So let's do that. But then I'm allowing my read to happen before I complete the write request, because read is has higher priority. Suppose we do that, and then x equal to 1 happen, and then reading from y happens. This is before y equal to 1 is finally able to get on the bus and invalidate everybody else. And finally, I acquire the bus, finish my write equal to 1, and boom, I get x equal to 0. So this cannot happen. This is not allowed to happen under sequential model. And the problem is I allow y to, quote, finish in the background. You cannot allow that to happen. Okay? The write cannot be considered to be complete until you get the bus. So that's the serialization. And why that? This is, again, we are assuming our processor supports sequential consistency. So you can see that I am constrained now what I can do. I cannot do this ordering thing. Otherwise, if I just look at P2, one processor, uniprocessor, in that context, it's perfectly legal to say, let's put y equal 1 in the background. Load from address x first, and then finish y equal to 1. You can't do that. Okay? So there is the notion of when a memory transaction completes. Okay? When does a write complete? Well, actually, I guess the simplest case to think about it is everybody has destroyed their copy from their cache. Invalidation has happened. There's only one copy in your cache. Then, of course, write completion already happened. But it doesn't have to be that way. Okay? We don't need to wait for the actual invalidation to happen. How so? All we have to do is to make sure that we get to the bus. There's a fine distinction between this transaction is committed versus it actually is completed. Okay, so commit simply means the design is such that we guarantee that it's going to happen in the future. So when we get to the bus, then what happens? We're going to drive this thing onto the bus. We say, please invalidate cache line X, and every other cache controller will take that into account. We'll put this into, I can clear this up, right? So we will get the address X over here, and it says, okay, please invalidate. From now on, the design has to be that we guarantee this is going to happen. And that's the commit. As long as we do that, we're fine. We guarantee that this has happened. It will happen. We don't actually know when this is done. Maybe 2 cycles later, maybe 3 cycles later, but all that it matters is that this is inserted into the destination processor's local order before the next transaction. So from a transaction point of view, this is order before next. We don't know which cycle, okay? And the same argument will extend to a more complex system. So if we don't have a bus, as long as we send the invalidation to someone, he may not process it immediately, but that node who gets the invalidation is committed to make that happen before the next action, before the next memory transaction. So this may take a little getting used to, but this is really what we do. We don't wait for the cache line to disappear or to be labeled as invalid in the cache in a realistic sense, but we use this commit. And also, this doesn't mean when we're supporting sequential consistency, doesn't really mean we have to do this in program order. We have to execute, we have to commit, we have to carry out memory transactions in that program order. We can still have speculative out of order processing. We just need to keep track of the memory operations such that it appears as if carried out sequentially. So this is a good time to perhaps refresh your memory on how load store queue works. Okay, so if you remember on a let's say we have a whole bunch of memory transaction load from address X, store to address X, load again from address X, store to address Y, load from Y, so on and so forth. So let's say that's the order: older, younger, right? This is your program order. And the address may be register. So the instruction may say load into R1, 0, R4. The address may not be ready, so we don't even know that it's X. We just know there are these load instructions. So what do you do, right? According to program order, this load, for instance over here, needs to return whatever value produced by that load. Okay, that's the idea. And this load has to return the value from the store. So suppose when we have all these instructions in flight, okay, and we don't even know, they're not ready, and the very first instruction that got ready was this instruction. What do? We can wait until all previous store instructions have finished, or at least have figured out their address, and then decide if we're going to forward from any one of these stores, or we can load speculatively, go to the memory and see what happens, right? But if that's the case, we will be loading some value produced before all these store instructions that we're seeing over here, right? And what if then, suppose we execute this load first, and then we realize there's a store? How do we know that we did it right? And that's where the load store queue comes into play, okay? One way to think about it is everything is recorded. So let's maybe give this guy some name. Let's call this 1, 2, 3, 4, 5. Okay, and then we have our entries. 1, 2, 3, 4, 5. This is in my load store queue. Okay, so every time an instruction executes, a memory instruction executes, let's say 5, we have to search for older, lower sequence number, okay, to see if I have an address. So suppose the address in question is Y. We have to search these memory operations to see if any one of them is a store. If so, if the address is Y. And if both is true, suppose this has already happened and we know it's to address Y. Oh, then we forward the data from 4 to 5. Okay? But suppose this hasn't happened yet. We don't know. Then what do? We load, we store anyways. Right? We store anyways. We find out so let's have maybe another bit, maybe some other entries. The load store queue keeps all the information, right? Let's say address, and let's say whether it's executed or not. Okay, so initially nothing is executed, we executed Y. Fine. And then the next thing happened is we execute store 4. Then we have to search in the opposite direction. Oh, I forgot to mention that this executed. So if we search in the opposite direction, what do we find out? Okay, my address is Y, this address is Y, it's younger than me, but it has already executed. What happens? Boom, this has to be squashed. This load executed incorrectly. Okay, it was unlucky. You have to try again. And for easy operation, you basically squash every instruction that follows that instruction and you restart from that instruction. You could selectively squash only the dependent instruction, but usually it's easier to squash everybody. So that's what load store queue does in a uniprocessor, to make sure that even though we executed all these things out of program order, that by figuring out who is accessing what address and whether they should get a load should get any in-flight stores result, we can restart anything that we executed incorrectly when we first executed speculatively. In real implementation, this is not really done as one gigantic queue. It's usually implemented as 2 separate queues because they keep different information. Load queue keeps all the load, store queue keeps all the store. They're slightly different in their content, but they all have fields such as address, whether it executed or not, and so on and so forth. So when you have a store, you go to the entry that marks all the younger loads and you search in that direction. And when you have a load execute, you find the corresponding age in the store queue. You search in the older direction to see if you need to forward data. Okay, that's what happens in uniprocessor. So with that refresher, let's come back to multiprocessor. Okay, we have to worry about sequential consistency. Now, if we have an invalidation seen on a bus, got an invalidation, I will search my cache tag. That's obviously what we do, invalidate any line and so on and so forth. But if we have any load issued prior to the invalidation and it's not yet committed, I need to search to see if it had loaded from the cache line that I'm trying to invalidate. And if so, that means it loaded too early, because now we saw the invalidation coming in. This invalidation, this, let's say it's a write to cache line X. Okay, then X, this transaction happened now because we got it. But the load that is still pending in my load queue, they're speculatively executed. They haven't been committed. They cannot be appearing as if it happens before this write X transaction. So if we find any, we may need to replay. Okay, it's a may because some complicated, because there may be some complicated optimization that you can say, we don't have to, we'll do this and that. But for simplicity, let's just assume we replay. And this is what one major processor implementation, while R10K does exactly that. Okay, so in an out of order processor implementing sequential consistency, we have to make sure that the result obtained are explicable under the sequential consistency. We don't need to actually carry out the memory transactions in the program order. Okay, that would be too restrictive. Okay, we can issue something early, but we have to abandon the value if it turns out this is going to violate the consistency, the sequential consistency semantics. And the idea is usually use the retire order. The execution order, when you execute it, doesn't matter because this is copying from uniprocessor. How do we maintain sequential semantics in order? We do in order commit or retire, whatever you want to call it. Okay, so we use that order. So by the time you commit or retire, you haven't seen any invalidation from another processor, then this early load is fine. You loaded what you would have loaded if you load at the retire time. That's sort of the idea, right? Let me repeat that. If a load is issued earlier, but it received an invalidation before it commits, that means if we pretend the load happened at the commit time, then the commit time would have encountered a miss and get a possibly different value, right? If it hadn't received an invalidation, that means if we issued it at the commit time, we would have gotten the same data. It's still in the cache. Okay, so for simplicity, if we indeed encounter invalidation prior to commit, we'll squash, restart restart the instructions from that point in time. Okay, and more specifically, this is our 10 case implementation. Whenever there's an invalidation, search the load queue, and you find a match. The address of the load falls within the range of the cache line. So what you're trying to do is to squash those instructions. But how is this carried out? It wasn't squashed at the moment, it was just marked. The entry of the load was marked. And when we are committing the load, when we're trying to commit the load that was marked in the load queue, that's when we squash. And the squash is done by doing what is called a exception, a zero handling action. We handle an exception, which is flushing all the pipeline and reload from that location, except we don't execute any exception handling logic or code. So we essentially just cleared out, restarted all the instruction. So here is a very complicated question. I strongly urge you to pause for a long time and think about it. Suppose I have this processor. R10K happens to be, or MIPS R10K is a MIPS processor. They use sequential consistency. Suppose I have an alpha processor. Okay, and I'm issuing a very relaxed consistency model. And my model says if you don't have any memory barrier, there is no sequential ordering whatsoever. The question is now, do you still need to do that? Do you still need to do what we just did? Think about it. Well, the answer is clear. You don't have to do this. Although if you did do this, what happens? You're guaranteeing sequential consistency. And therefore, if you can explain the program according to a sequential consistency model, you of course can explain the program as the outcome, as a legitimate outcome under a relaxed model. Okay, that's easy. But you have to, you don't. You don't have to. So if you checked for this condition, you would have issued some, maybe not a lot, but some replays that are unnecessary, that your model allows. Your model is more relaxed. Okay, it allows this out of order. So you load it early, so what? You can explain it. You say, wow, I loaded this early because I'm allowed to. That's in our written contract of the memory consistency model. So the idea is you don't have to do this. But do you have to do anything? Pause again, think about it. I'll give you a hint. Remember what is cache coherence? What are the two conditions? What is memory consistency? What are the two components? So the answer to the question whether you need to do anything is that you actually have to do something. It's a little complicated, we'll explain here. Even if you have the most relaxed consistency model, remember what you have to do. You have to guarantee cache coherence. And what is part of the coherence contract? I shouldn't say contract. What is part of the requirement for coherence? It's write serialization. Okay, so even though you have relaxed consistency model, you have to support write serialization. Okay, what does that mean? What is the implication? Here is one example to show that. On the one hand, on the left hand, I have two reads. Okay, loading from address x1, loading from address x2, and it so happens that x1 and x2 are pointing to the same location. Okay, and y, that's the location y. So on the other hand, I have y equal to 1. That's a write. So think about this. Again, assuming everything is 0 to begin with, so y is 0 in this case. In this code, what are possible outcome when I print out? Let's say at the end I print out both R1 and R2 at this point. What are legal outcomes and what are not legal outcomes? Pause the video, think about it. So this is the answer. Why? Okay, because in write serialization, the access, the write to the same location has to be uniquely ordered, globally ordered. Everybody has to agree to that order. Okay? Which means write to y. Okay, it happens at some point. Doesn't matter when. Okay, but it's either before these transactions, in between these transactions, or after these transactions. Okay, so the observation of the same memory location, these two transactions, these two reads from the same processor, they either can read both the new data or both the old data, or this reads the old data, but this reads, the second one reads the new data, not the other way around. Not that the second reads the old data, R2 reads the old data, and R1 reads the new data. That would violate write serialization. Okay, so you have to detect this. Even though you have a relaxed consistency model, you have to detect this. How do you detect it? I'll tell you how IBM's processor did it. Okay? There are a couple of ways of doing it. All right? Let's just think about this for a moment. Let's say I implemented sequential consistency, R10K. So this, maybe this executed earlier, so it got a 0. This executed earlier. And then, so this happens first, this happens second, and this happens third. Let's say that's the case. In R10K, what would happen? Well, I would be reading a 0 here, and when transaction 2 happens, this would be searching for my load queue in this processor, because this hasn't committed. That operation hasn't even happened yet. I cannot commit. By the way, I forgot to say it's program order: first instruction, earlier instruction, later instruction, right? So when I search my load queue, okay, maybe I should draw this out. So I have my load queue. This is the X1. This is X2. Executed. Yes, this one is executed. And then at time t2, this happens. I'm going to do a search. Okay. This is not there yet, but X2 is there. We know that this address is the same as Y. And it has executed. So what? We're going to invalidate or squash all the instructions from that point on, right? And then that's fine. Then when both execute again, this and this both will get the new value, and that's legal. This is a legal outcome. So you can implement a stronger order. There are lots of things you can do. You can always issue load in program order. Never issue them out of program order. Then this will, the illegal operation, the illegal outcome will never happen. Right? So there are lots of things that you can do, but what is the thing, what is the most relaxing, what is the highest performing, shall we put it, the highest performing approach, which is you allow as much out of order processing as possible and catch only the thing that is not allowed. Okay? So paradoxically, maybe not paradoxically, but counterintuitively, what you have to implement in a relaxed consistency model is slightly more difficult to catch. Why is that? Because in a relaxed consistency model, the condition of being wrong is more stringent, because it's you got a more less constrained description of your system. You can do a lot of ordering. Okay, right serialization is harder to violate than sequential consistency. Okay, it's very easy to violate sequential consistency because it's a very strong model, very restrictive model. But right serialization, it really has to have all these things happen for it to be wrong. And this is how it's done. It's not the only way that you do this, but this is how it's done in one of the processors. Specifically, it's a power processor. And this is because we recognize you have to have all these conditions violated. First, 2 loads have to execute out of program order. Again, if all your loads are executed according to program order, you will never violate right serialization. Okay? And after that, in between the two loads, they executed out of program order, and in between the 2 loads, which are executed out of program order, there's an invalidation from another processor. And thirdly, all of them have to be to the same location. Okay, if these are two different locations, again, this is totally valid. So here's what happens, right? The example over here, program order R1, R2. Okay, and there is a write transaction on P2. And in actual time, the younger load executed first. In the older load executed later, and in between the invalidation comes in. Okay, that's the, if you want to detect the combination of all three, it's actually fairly tricky. At any time point, at this time point, at this time point, you will not be able to say you violated write serialization. No, not necessarily. It's only after the third transaction happened do you realize all three conditions are met, you have a problem. Okay, so here's the cartoon. I have my load queue right here. Okay, it's from older to younger in program order, from in that direction. So what happens when I issue my read into register 2? Let's say it's here. Oops, sorry, it's here. I simply record it. This R2 is not there. This is just for me to show you that this is the second read. All we're recording is really that it is to memory location Y. And the next thing happened, let me clear this and go back. So the first thing that happened is a read, which is fine, we record it. Next thing happened is a write from another processor, which happens as an invalidation. When we have an invalidation, we search the queue. Recall that in a sequential consistent machine, we already know that this is bad idea. We can already squash this instruction and so on. But now we don't know that this is wrong. This might be fine. When do we know it's not right? That we find there is a new instruction. There is another load to the same location, but it's actually younger. When we execute that load, the older load getting the younger value, getting the newer value, that's bad. So how do we even know that that happened? When we issue a new load, okay, we cannot just execute it, because this time if we execute, we'll just load. Here, if we do a load, because it's already invalidated from the cache, we'll have a miss. We go out to the memory system, we get the intervention, we'll get the new value. And that's the problem. So at this time, we need to search to see if any younger loads has executed. Okay, so we need to search the load queue again, not because of any local out of order reason, but because of write serialization. We have to search through to see if there is any younger loads after us that has already executed and has that dot set. This dot really means that not only it executed before the invalidation. So when we see that dot set, we have to squash. Okay, again, let me clear this. When we issue a load, we only need to record it. Nothing is wrong. When we get the invalidation, we search and we find a match. That in itself is not a problem. Therefore, we cannot squash it, or we, let's say, it's not that we cannot, we can squash it, that would be too conservative. So what we do is we mark a bit to say dangerous. And only when we have an older load executing, searching for younger loads in the system, and finding out that this bit has been marked, do we need to actually squash that instruction and all subsequent, or at least dependent instructions. Okay, so enforcing write serialization is actually pretty difficult, because it's sort of perhaps a poor analogy is this: if you're a policeman, it's very easy, let's say, to detect someone is texting while driving, or someone is speeding while driving. Okay, detecting those are easy, and you can just stop them, give them a ticket, whatever. But let's say we have a relaxed traffic law that says you can text while driving, you can speed, but you cannot text while speeding. Then the job for the policeman is actually more difficult. And this is the case here. So the police, the load store queue, at least in the case of Power 4, was not trying to capture a broader category of offense, but a narrower category of offense. Only when all three conditions are met do you have a real problem. Of course, you can conservatively squash more. You would just be slower and guaranteeing correctness. Okay. So that's, you see, that's where the design of the microarchitecture itself actually has a lot of influence because of the coherence model, because of the consistency model that you're supporting. And this is actually bad. So not all processors do that, do this very, very specific check. For instance, Alpha 21264 only checks condition 1 and 3. Okay, so in that case, what happens is the minute I find two memory accesses, two loads to the same location happened out of program order, I squash the younger load. I don't care if they got different result and the newer one got the younger one got the older value, and so I don't care. I don't care if condition number 2 happened. I conservatively flush. You can do that, okay? And that's exactly what was being done by 21264. But in any case, this goes back to, remember how we describe uniprocessor. In the uniprocessor, load store queue. A store searches for load queue, a load searches for store queue. But in fact, a load needs to search for load queue as well. And this is a problem. Why is it a problem? Because a queue, a content addressable queue, just has, the more port you have, the bigger the cell. This is your conventional 6T6 transistor memory cell. Okay, you can think about it as having an access transistor pair with a cross-coupled inverter. When you're doing a search, you're actually doing something like this in the access transistor to see if it happens to be certain pair. And if there's a match, if anyone is a mismatch, then you drain the match line, and then the match didn't happen. So you have these transistors to do searches, and the more transactions, the more cases you need to search the load queue, the more ports you need, for instance. And if you allow 2 memory transactions per cycle, then you need to be able to support 2 write ports to it, because every load needs to be written into the load queue to start with. And you also need to have a lot of search port, because every load needs to search everything before it. So you need a search port for the load, and you need to have one for the invalidation. So that's going to give you a lot of transistors per cell, which makes it slower, which makes a bigger structure even slower than that. So this is a problematic thing. Okay, in the next video, I'm going to explain something that you can skip completely. It's an optimization. It just goes to show that there are lots of things you can do. It's always a trade-off, and you can decide whether the trade-off is worthwhile or not.